Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today I am going to discuss the topic of finding residues using Laurent series as a part 2. So in the last session also we have discussed the same topic, and today again we are going to find the residue of a function at a point z equal to a, at a pole z equal to a, which can be obtained by finding the Laurent series expansion of f of z and then the quotient of 1 by z minus a. That is the residue of the given function. So let us solve some more examples on the same topic. Now coming to this problem, f of z is 1 by z square minus 1. So we need to find the poles and residues of this function. We need to find the poles and residues of this function using Laurent series expansion. So first we can write this as 1 by z minus 1 into 1 by z plus 1. A plus b into a minus b, which is a square minus b square. So this is z square minus 1. And by splitting into partial fractions, this is equal to half into 1 by z minus 1 minus 1 by z plus 1. So by resolving into partial fractions we get this, that you can find the partial fractions. Now, so 1 by 2 into z minus 1 minus 1 by 2 into z plus 1. So here, in fact, by equating the denominator to 0, we get z minus 1 into z plus 1 is 0. Z minus 1 is 0 or z plus 1 is 0. So z equal to 1 comma minus 1. These are the poles of the given function. Now we need to find the residues at these two poles using Laurent series expansion. So first we need to expand the function as a Laurent series. Now first residue of f at z equal to 1. So here we have to expand f of z as or as a Laurent series about z equal to 1. That means in powers of z minus 1. So put z minus 1 equal to w. That implies z is 1 plus w. And what is the function f of z here? 1 by 2 into 1 by z minus 1 minus 1 by z plus 1. So z minus 1 is w. 1 by w minus z is 1 plus w. So here we get 2 plus w. So this is half into 1 by w minus 1 by, here we need to have z minus 1 powers. So I will take 2 common, 1 plus w by 2. So 1 by 2w minus 1 by 4 into 1 plus w by 2 power minus 1. That's equal to 1 by 2w minus 1 by 4 into, expand this using standard expansions, 1 minus w by 2 plus w square by 4 minus w cube by 8 plus so on. So this is the final expansion, or we can simplify this by multiplying with 1 by 4. So plus minus 1 by 4. So plus w by 8 minus w square by 16 plus w cube by 32 and so on. Now replace w by z minus 1, and what we get, 2 into w minus 1 minus 1 by 4 plus w is z minus 1, and here also z minus 1 by 8 minus z minus 1 whole square by 16 plus z minus 1 whole cube by 32 minus and so on. So here we are calculating the residue of the function at z equal to 1. So that means the residue of f at z equal to 1 is the quotient of 1 by z minus 1. Now what is the quotient of 1 by z minus 1 here? 1 by 2. Similarly, we need to find the residue of the function at z equal to minus 1 also. So residue of f at z equal to minus 1. So that means we have to expand f of z as a Laurent series about z equal to minus 1. That implies in powers of z plus 1. So put z plus 1 equal to w. That implies z is w minus 1. Now f of z 1 by 2 into 1 by z minus 1 minus 1 by z plus 1. Now z is w minus 1. So w minus 1 minus 2 minus 1 by w. So which is, here we can take minus 1 by 2 common, so that 1 minus w by 2 minus 1 by w. So this is minus 1 by 4, 1 minus w by 2 whole inverse minus 1 by 2w. And by expanding this using the standard expansion, 1 plus w by 2 plus w square by 4 plus so on minus 1 by 2w. So f of z is minus 1 by 4 minus w by 8 plus w, since the quotient is minus 1 by 4, all the terms are minus, by 4 into 4, 16 minus and so on minus 1 by 2w. Here w is in the numerator in the remaining terms except at the last. So replacing w by z plus 1, we get minus 1 by 4 z plus 1 by 8 z plus 1 whole square by 16 and so on minus 1 by 2 into z plus 1. So residue of f at z equal to minus 1 is the quotient of 1 by z minus a. Here a is minus 1, z minus a is z plus a. So that becomes z plus 1. So the answer is, this is the 1 by z plus 1 term and the quotient is minus 1 by 2. So like this, by expanding the given function as a Laurent series, we can find the residue at a given pole. Coming to the next problem, here f of z is e power z by z minus 1 whole square. First expand this as a Laurent series about z equal to 1 and hence find the residue at that point. So about z equal to 1, that is in powers of z minus 1. So put z minus 1 equal to w, take the substitution, then f of z becomes, then what will be z? 1 plus w, e power 1 plus w by z minus 1 is w square. So e by w square into e power w, e by w square into 1 plus, this is the expansion of e power w, exponential function, w square by 2 factorial, w cube by 3 factorial and so on. So therefore f of z is e by w square plus e by w plus e by 2 plus w by 6 plus so on. So what is w? Replace w by z minus 1. Then we get f of z is e by z minus 1 whole square plus e by z minus 1 plus e by 2 plus w by 6, w means z minus 1 by 6 plus so on. So therefore, now we are calculating residue of f at z equal to 1, which is the quotient of 1 by z minus 1. 1 by z minus 1. Now, where is that 1 by z minus 1 term? That is E. So, the answer is E. So, in today's session, we have calculated the residue of the given function using Laurent series expansion. And using the Laurent series expansion and finding the quotient of 1 by z minus a, we can find the residue of f at z equal to a. So, to find the residue, we can use either the formula or the Laurent series expansion. So, in the next session, we are going to discuss an important theorem called residue theorem, which is also known as Cauchy's residue theorem. So, using the Cauchy's residue theorem, we can evaluate the given integral of a complex function, integral from f of z dz. This can be calculated using this residue theorem that we will discuss in the next session. Thank you very much.